Okay, let's get back into business. So the great thing about going beyond material normally covered is that now I get to choose what is covered or like what I teach about, and I want to get to some really cool stuff. So we'll do one more extremely easy, not one more, one extremely easy NP-complete problem. Then we'll move on to space complexity. Space. Portal jokes, anyone? All right. So one problem that's kind of like clique problem, but sort of the inverse problem is called independent set. So this problem, independent set, and I'm going to abbreviate it as IS. So this problem is exactly the same as clique, but among the k vertices, there is no edge. So for clique, it was a complete subgraph. Every single edge is there. But here, there is no edge among those k vertices. So like these vertices are completely independent, hence the name, of each other. Okay, so just as an example, if we have a graph, I'm not going to draw the whole thing, but if we have a graph like this, so these four vertices have edges going elsewhere. They don't go to these four vertices. So now in this graph, we can say there's an independent set of size 4 because among those four vertices, there is no edge. But yeah.
I don't know how this would fit in. Would there be an independent set for one vertex? It has technically no edges, but it's also
yeah, so any isolated, there's always an independent set of size 1. Mm-hmm. Yep. But independent set of size 2 is just any two vertices that have no edge. 3 vertices, there's no triangle, and 4, there's no complete subgraph, 4 vertices. Okay? So I want to show that IS is NP-complete. So we know the drill at this point. To show that IS is a member of NP, how do I show it's in NP? Yeah, a certificate, and what would the certificate be in this case? Yep, exactly. Yeah, this part, it really is the easy part. It should not be hard. Certificate is the set of k vertices, and we should just be clear about it, having no edge among them. And now we just got to show IS is NP hard. Okay, well, now we have a whole host of problems to work with, right? We have CNF sat, we have 3 sat, we have clique, we have vertex cover now. So any choice of problem that seems closest to this one. Well, vertex cover is pretty close. It has graphs in it, but is there one that's closer? Clique. Oh, why should we pick clique here? We can invert it, right? If there's a clique of k vertices, what if I just made it so that for every edge that's there, make it not there, and every edge that isn't there, put it there, or what is called complementing the graph. Then, if there was a clique on k vertices, now there's an independent set. Okay? So we'll show that clique reduces to IS. So given a graph G, what's the easiest way I can say this? Form the complement graph. We'll call it G bar, which is the complement of the edges of G. Since this one is a lot shorter, maybe we should put analysis as to why complementing the graph actually does give us a clique if and only if there's an independent set in the resulting graph. So suppose G has a K clique. Well, that means that, does G bar have a K clique? Oh, sorry, K independent set. Yes, because complementing the edges means that if it had a K clique, it has an independent set of the same size. So this implies G bar has a KIS, I'll say, K independent set. Well, now let's look at the other direction. Suppose G bar has a KIS. Well, if the resulting graph has a K independent set, did the original graph have a K clique? Yeah, because if we just complement again, we get the original graph back, which by nature of having an independent set, the complement is a clique. So G has a K clique. Okay, so NP hardness proofs are not necessarily very difficult. Some of them are harder than others, but some of them are just complement the graph or do some really minute change. Okay? Any questions? About NP completeness or any of that? Okay. So I think it's now time to look at a brief overview of what we've seen so far. So let's assume that P is not equal to NP. So if we assume that, then we have problems in P that we know and love. Then we have problems in NP, such as let's assume P is not equal to NP. Then 3 sets out here, clique is out here. Right, that's the view of the world that we've seen so far. And for instance, all regular languages are in P because we can verify them in linear time. It turns out all context-free languages are also in P via some a dynamic programming algorithm, which is illustrated in the book. But maybe we want to think about, okay, are there some problems that are harder, supposedly, than even in NP, or even harder than NP-complete, right? Maybe there are some problems of that nature. And then maybe we want to also think about, well, maybe if we have, instead of a lot of time, we have space, like a limited amount of space, but we don't eliminate the need for time. So we have a constrained amount of space, but we forget about time altogether. And maybe, for instance, you have, maybe we can talk about an efficient amount of space, which means polynomial space, but even say like n squared space, in general, that is too much for some of the problems that we have to deal with. Like for example, one of the graphs that I used in my thesis had around, what was it? It was like 32,000 vertices, and storing the adjacency matrix of that graph was around 5 gigabytes in size, in the most compact representation I could find. And processing it took 2 days each, and I had 27 of them. So maybe instead of talking about a polynomial space, we can talk about a very small limited amount of space. For example, if any of you work in big data, maybe you have this stream of data, maybe tweets that are posted. You can't store all that information, right? It's just flowing by too fast and it's just too much for your drive to store. So maybe what you can do is you can talk about an extremely small amount of space and what you can do with that. And so that's what is called logarithmic space, and we'll hopefully at least take a look at that. But for now, let's look at an efficient amount of space, which is polynomial space. Okay? Any questions before we move into space stuff? Okay, so let's talk about space. So we defined this function time before for how long a particular language takes in order to have a Turing machine compute for that language. So remember we defined, just as a thought, we defined time of f of n to be set of problems or languages decided in O of f of n time. That's what we defined maybe last time or 2 times ago. Okay, well, let's try to do the same thing here. So we're going to define space of f of n. Well, we gotta be a little bit careful here because time, that's pretty fundamental to a Turing machine, and we can actually count that. But remember, when a Turing machine receives some input, there already is some space being taken up. And also the tape is a one-way infinite size thing. How do we talk about space in that setting? So maybe what you can think of is, we can think of space as how much you actually use of the tape, and such that everything to the right of you is all blanks. So you haven't really used that stuff yet. So we'll define it as how much space is actually used on the tape. Okay? Well, if we... At
the greatest point in time.
Yes, at the greatest point, yeah. So it's the maximum, so if we think of O of f of n, that's the maximum used on all inputs of size n. So this is the set of problems decided in O of f of n space for all inputs of size n. And we mean this as the furthest right cell reached on the tape, either through putting the input on the tape or via simulation. So now it extends to space pretty easily. But we can also talk about non-deterministic space, which will actually turn out to be really useful in this setting too. So we'll define n space of f of n to be same thing on a non-deterministic machine. So for example, all regular languages are in space n, because it's actually better than that. But we can definitely just store the input and then just scan across the input. We don't need any more space than what's provided on the input. So therefore, all regular languages are in space n. They're also in time n, obviously, but they belong to space n. Okay? And just like before, we defined p to be all polynomial times. We're going to define p space here to be all polynomial space. Okay? So we're going to define p space to be almost exactly the same as before, but for space n to the k. And in the same thing, I'm going to put NP space for n space. So if you want to talk about non-deterministic P space, that's just non-deterministic space for all polynomials. Okay? Exactly the same definition as before, but with space instead. Okay? And one cool result we'll see right away is that NP is a subset of P space. So here's a theorem. So what I'm claiming here is that any NP problem, including NP-complete problems, can be solved in a polynomial amount of space deterministically, even if it's non-deterministic. Well, how can I do that? Well, let's see. If I show you that I can solve some NP-complete problem in polynomial space, does that mean I can solve every NP problem in P space? I think so, because if any problem can be Pauli reduced to that problem, then it's only polynomial size larger, and then therefore, if I can show it can run in P space, it's some polynomial times another one, and so therefore it runs in polynomial space too. Just a much larger polynomial, but we don't care about that. So any problem that we could, is there any problem that we can run in polynomial space? Is there one that you want to run in poly space? CNF-SAT, that is the one we'll do. So show CNF-SAT is in P space. So here, remember, we can reuse space, but we can't reuse time. Okay? So what is a simple algorithm that will always work to determine if a formula is satisfiable? Well, here's one. Just brute force everything. Try all false, then set the first guy to be true, then false true, then false true true. Yeah, so just try all 2 to the n combinations. Well, if I wrote every single one of those on the tape, will I use more than polynomial space? Will I use more? Well, there are 2 to the n different assignments.
Are you saying not reusing?
Yeah, I'm just saying write every single one to the tape. Then I'll use 2 to the n space at least, right? Is that more than a polynomial? Yeah, that's more than a polynomial. It's exponential. So that idea won't work. Is there an idea we can try, though? Here's one. Write one assignment down and check if it satisfies. If it doesn't, erase it, then write down the next one. If it doesn't work, erase it, and then keep going through all the other assignments. Will I use more than polynomial space that way? Well, The formula size I got to keep somewhere, so that's only that's polynomial size. The assignment size, that's only polynomial size, so that's fine. What about the result, or computing the result of the formula? Well, that can only be polynomial in size too, because it's just a single number, 0 or 1. So in total, that's a polynomial amount of space. So the idea is try each variable assignment in turn and delete previous assignment. And we can see that this runs in polyspace. Okay, so therefore NP is a subset of P-space. What about P-space and NP-space, the non-deterministic version? Well, NP-space is definitely at least as large as deterministic space, because I don't have to use non-determinism, right? So it's definitely at least as large. Okay? Well, because we don't know whether P is equal to NP or not, we don't really know how to relate deterministic time and non-deterministic time, right? Because if we did, then we can actually then say something about P and NP. What about space? Do we know something about deterministic and non-deterministic space? Well, since we can reuse space, maybe what we can do is simulate one possible set of choices that the non-deterministic machine can make, and if it ends up not working, backtrack and then try another one. Backtrack and try another. Okay? So since we can reuse space, maybe we can actually say something about deterministic space versus non-deterministic space. And that's what we're going to do right now. So we're going to prove a result called Savage's theorem. So savage. All right, well, it doesn't really make sense yet because we haven't really defined it. If we have space that's less than the size of the input, because that really doesn't make sense yet. We'll define it maybe later, but we're not going to define it now. So we got to talk about space that is at least as large as the input. So when f of n is at least n, we got to have it be at least as large as the input. Then we want to say something about how large NP space of f of n can be.
That quotation kind of seems a little weird. Like the n, the f of n is greater than n.
Yeah, if this function is at least n. Yeah. It could be like n log n or whatever. Mm-hmm. Well, what this result shows is that you don't get a whole huge increase in the deterministic space sense. So if you have a non-deterministic space machine and you wanted to convert it to a deterministic space machine, you don't pay a huge penalty. Whereas for time, you may end up with exponentially more time than what you started with because of just trying all possibilities. But since we can reuse space, we get a result which is this. We get that NP space of f of n is contained within space of f of n squared. And as a result, if we have an NP space machine that runs in non-deterministic polyspace, well, if I square whatever that polynomial is, that's also a polynomial, which means that P space is contained within NP space, but that's contained within P space. So as a result of this, we have that P space is in fact equal to NP space. Okay? Cool, so let's prove this. Well, we got to prove it in the general case. In the general case of f of n, it may not be polynomial, it may or may not. It may be more, it may be less. So let's consider a non-deterministic machine running in f of n space. Because our idea is to convert that non-deterministic machine into a deterministic machine that only uses the square of what the original did in terms of space. Okay? So in order to help us here, we're going to think about trying to do a simulation deterministically. Okay, so we're going to think about, I have this non-deterministic machine, and I'm trying to simulate it deterministically without using too much space, f of n squared space. Well, how are we going to do that? Well, we want to ask the question, if I'm in some configuration of the original machine, can I get to some other configuration within some number of steps? And then if we apply that inductively, we can ask, can I get from the first configuration to an accepting one in not too many steps? So if we solve the subproblems, we can solve the bigger problem. So we're going to define a function can yield. I don't know why everything's in caps, but yeah, it's yelling at us. So it takes 3 arguments, C1, C2, and T, and is true if, let's see, if there is a computation from config C1 to C2 in at most T steps. Because remember, if I try to store all possible non-deterministic paths that this non-deterministic machine may take, that may be exponential. So we got to be a little smart about this. We got to be able to store previous results in order to help us here. So let's implement can yield. In the general case. So we're going to approach this in a very merge sort-like structure. So if T is 1, then that means that within one step, you can reach C1 to C2. Well, that's only true if they are either equal or you can reach from C1 to C2 in one non-deterministic step. So that's easy. But in general, if we have a C1 way up here and a C2 in here, suppose we can reach from C1 to some configuration in the middle, and from that guy, we can reach C2 at the end. Would that mean I can get from C1 to C2? Yeah, so that's the structure that we're going to do. But instead of storing everything along the way, we're going to only store the can yields of each. And then once we know the inner subproblems, we'll delete them. And then look at the outer one. So if T is 1, check if C1 is equal to C2 or C1 yields C2 in one step of the non-deterministic machine. But there's a problem here. Well, our idea is good. We want to be able to get from C1 to C2, from way up here to way down here, by finding something in the middle for which, if I can get from here to the middle one and the middle one to the end, then I can actually figure out I can get from C1 to C2. But how do I get to the middle one? Or what is the middle configuration? I don't know.
It's like the rule generator thing,
Right. So I don't know what the configuration in the middle is going to look like. If I had a non-deterministic machine, I can just guess it, right? But I don't have a non-deterministic machine. I'm trying to simulate it deterministically. So what can I do? Yeah.
You have like another thing on the side, or like
For what?
like storing like doing deterministic, go through it, and then find like some random middle value, and then store it somewhere else, and then like go erase the original one, and then start over with that.
Yeah, but how do I find what the middle value is? I don't know what it is. Can I try all of them? Yeah. I'm not bounded by time. I'm bounded by space, but I'm not bounded by time. So look at every possible middle configuration and try all of them. Okay? So that's what we're going to do. So if T is more than 1, then for every config C prime of length, well, I better bound it by f of n, because, and that's good because there's no need to check anything longer than f of n because I know that the machine runs in f of n space. So that gives me a nice bound there, so I don't use too much space. Then for every single one of those, I'm going to split the computation in half. So I'm going to figure out, can you get from C1 to C prime, and can you get from C prime to C2? So if, run can yield from C1 to C prime, and it's in the middle, so hopefully I get there within T over 2 steps. But T over 2 may not be an integer, so I'm going to round down. It actually won't make a difference, but I got to make it be an integer. And second step, do the same thing, but from C prime to C2, and I'm going to make it ceiling of T over 2. So that when you add them up, it becomes T, because I better make it exactly that. Well, suppose that the first call says yes, and the second one says no. Can I get from C1 to C2 now? No. Both of them better say yes, and then therefore we're good. So if both calls accept, we'll accept. But if all configs were tested and none accept, we'll reject. Yeah.
Would there be a case of where some configs, or all configs were tested and some of them passed and others failed?
Yeah, certainly. I may have some configs in the middle that are bad configs where you can get from one to the other, but not the other one. That means I can't get from C1 to C2, and I should not allow for that, yeah. But if I try every single one and none of them work, there's no way I can get from C1 to C2 anyway. Yeah.
Like just like visualizing it, is it like all in from like a tape or something? And then is it for two?
Yeah, so what we're doing is we're keeping track of C1 and C2, and then we're going to keep track as a third configuration, all possible configurations. And then we'll keep the result of can yield over here, from C1 to that guy and that guy to C2, or however you want to implement it. Yeah, we'll analyze the space in a second. Other questions? Okay, well, now we just got to run the original problem. So what is the time bound that we need to run in general? Well, let's see. So let C start be the start config. And the problem here is that I don't know for an accepting configuration what that configuration is going to look like, right? It's going to have QAccept in there, but I don't know what the rest of the tape is going to look like in order to figure out can yield from the start config to that final one. So again, let's just try all of them, right? There's nothing wrong with that as long as I don't use too much space. So for every config, of size at most f of n containing QAccept, let's call the config C double prime, because we got to give it a name. Okay, well, now we just got to figure out how many steps could it possibly take for me to get from this start config to the ending one. So let's see. We'll run can yield from C start to C double prime. But remember, the machine that we have here is a non-deterministic polynomial space machine. We don't know how many steps it'll take, which is the time part of it, right? But how many steps could you possibly take in f of n space? Well, let's see. It's a constant number of cells that could appear in the first cell, constant number of cells in the second, constant number of cells in the third, all the way to f of n. So it's just an exponential number in terms of f of n. So here we'll just put 2 to the O of f of n time. Because I can't use more than that amount of time if I'm restricted to f of n space. The constant depends on what can appear on the tape, but we're not necessarily worried about that. We're worried about how much time asymptotically does it actually take at most if you use f of n space. And we note from the linear bounded automata when we talked about that, we just simulated all possible configurations of the machine. We're doing the exact same thing in principle here. We're just saying you can't run longer than this because if you do, you will run forever. But we know we only run in a polynomial amount of space. Okay? And that's it. So let's just recap on this result. So Savage's theorem says if you use f of n's non-deterministic space, then you only use f squared of n deterministic space. And as a result, p space equals np space. So what we did is consider any non-deterministic machine running in that amount of space. Can we make a deterministic machine running in f squared n of space? Well, what we wanted to figure out is we're trying to simulate this non-deterministic machine. In order to do that, we got to apply transitions of the machine. And it would be really helpful if I can determine for two arbitrary configurations if one can reach the other in some amount of time in terms of number of transitions to apply. And we noted this recursive function can yield to mean you can reach from C1 to C2 in at most t steps. We'll analyze the space used in a second. So the idea here is that if you can find the middle element from these two arbitrary configurations and figure out you can reach that middle one from the first and from that middle one to the second via non-deterministic transitions, then you should say yes. And at the end, we just say for the start configuration and every possible ending configuration, can you get there in at most 2 to the O of f of n steps, which is the most amount of time you could possibly use. Okay? Well, let's see. What about the space used? Well, let's see. Well, we called this function with 2 to the O of f of n space. I gotta store that number somewhere, right? And it's an exponential number, so maybe I'm using an exponential amount of space right now to even store that number. Or am I? No, what should I do to avoid that? Well, how can I store a number really efficiently? How about binary? Yeah, binary. If I want to store a number n, it takes in binary some constant times log n space to store it. Well, if I have this number 2 to the constant times f of n, the log of that is just the stuff up top. So it's just constant times f of n. So the number here is constant times f of n. So this is for the storing t initially. Well, storing the original the start two configurations, the start and the ending configuration, that takes polynomial space. It's not polynomial, f of n space for each at most. So therefore, I can just swallow them up in the O notation. Well, for can yield, we may have a chain of things that may happen. I will do halfway through. So from the start to the ending one, I look halfway through. But then I got to look from the halfway point, store it there, and look halfway there, then look halfway there, look halfway there. So in general, whatever I had to start with, I may multiply by the log of the total amount of time. Well, what is the log of the total amount of time? Well, the total amount of time is 2 to the O of f of n. And the log of that is constant times f of n. So for the recursive part, I may get an f of n multiplicative factor. So this is for the recursion. But for once I get the can yields out of the way, I can just store those 2 bits, which is a constant amount. And once I go to a higher level up, once the recursion goes back up, then I don't need to store that bit down there anymore. So I'm reusing space. So in fact, this is all the space I need to store the initial thing for the time, as well as the original 2 configurations, as well as for the recursion. And so that gives us f of n squared space. Okay. Pretty cool result. So we can actually relate any amount of space, at least n, with non-deterministic space quite easily. You can actually see that if we want to think about exponential space versus non-deterministic exponential space, those are the same via this theorem, because you only get a squared amount. Or, yeah, any language class where if you square it, you still get in the same class, the non-deterministic version is the same. So we can actually talk about non-deterministic space and deterministic space and relate them really easily, but we know nothing about time. Okay? If any of you prove it for time, you should let some people know. Because then you may or may not prove P equals NP. Any questions about that? I know that was a lot. No. Well, I'm not savage. Or at least I don't think. This was proved in the 70s, I believe. But my thesis was about graphs and Arctic ice and all that stuff. I was just relating it to a practical application of like, even if you think of n squared, because that's for an adjacency matrix, that still is too much for some applications. And so we'll turn to logarithmic space next time. After we define P-space completeness, I'll try to think of some cool things for next time. Any questions? All right, I'll see you on Friday.